is this adapt and old or start from scratch and make a new? Adapt and old. You definitely don't want to do derivatives on there. It would be a mess really fast. Do you agree? Okay. If you get into the problem and you start taking derivatives and you start thinking, surely they don't want me to do all these derivatives, the answer is probably, yeah, you're right. They don't want you to do all the derivatives. You're probably doing it wrong. There are a lot of college professors that think rigorous means just unbelievable amounts of tedium. Can you wade through all this crap without making a mistake? That's their definition of rigor. That's not the AP definition of rigor. Rigor is high-level thinking in an AP test. So they're never going to ask you to just slog your way through some tedium. That's not the AP test, okay? So I, from experience, tend to make mistakes if I go too fast. So I went very slowly and methodically. I started with what I knew to be true, 1 over 1 minus x, yay? What do you put into that? Forget the 2x. That comes later. Negative x squared, right? You could do, I did the negative x squared in 1. So I rewrote this, but with parentheses instead, right? And then instead of putting in an x, I put in a negative x squared. You down? All right. Now at that point, then I choose, all right, should I take some time to clean that up? What goes through my mind there is, you know, if I'm going to need this later, it probably behooves me to clean it up. So I clean it up a little. I said that's the same as 1 minus x squared plus x to the 4th minus x to the 6th, and so on. Now this, I can tell you, this from experience, you might not have done, but it's usually something you want to do. When you get a negative, complicated here, you probably want to separate that into 2 terms. Integrating this later would be a mess if that negative is in with the x. Can you imagine if I kept it here and I integrated it, and all of a sudden I have this u-sub problem. It's ugly. So if you get something like that, I would recommend you split the negative off and the x you clean up separately. Didn't have to though. Then I multiplied by 2x. I multiplied by 2x, that's all. So you take that series and you multiply each term by 2x, distributing 2x. So at the end of the day, did you get an answer of 2x minus 2x cubed plus 2x to the 5th minus 2x to the 7th? And the general term could either be this if you simplified it, but if you did absolutely no simplifying and you had negative x squared n times 2x, that's okay. You can have that. It doesn't have to be cleaned up. So that said, let's talk grading. 1 point, they didn't, because you could have taken derivatives and guided your way through it, they didn't do any partial credit for the substitution because you didn't have to do it by substitution. This is how they graded it. In the first 4 terms, if you have 2 of the first 4 terms correct, you earn 1 point. If you have all 4 terms or the other 2 terms correct, you earn 2 points. And 1 point was for the general term or something equivalent to the general terms I have. So that was 3 points. 1 for the 2 of the first 4 terms correct, 1 for the other 2 terms correct, and 1 for the general. Are you all working on the 9 still? Are you still in? Yes. It does not matter, so that's a good question. Different colleges focus on this differently. Some colleges, it's all about summation notation, and in those cases, it's definitely n starting value is important. On the AP test, it's almost always expanded form, and the general term is just kind of floating, and that's just on that's on you to know what n is starting at, but they don't care. That said, if you're smart, you want to verify your general term works, and to verify your general term works, you need to go back and verify it's making these, and that you do need to know. So to answer your question, it's only for you to know what n needs to start at, but you should verify it.
So I guess with that take, you could say there could be
Oh, so there could be infinitely many here, and that's part of why they have math people, not computers, grading this, because they have, I mean, these graders do calculus all day for a week straight. I mean, they're doing different people's approaches, and there's some person that goes way out there. They might have to take it up the chain to say, hey, what do you think about this? So yeah, There's a lot of possibilities there to answer your question. The second one, I puzzled over for a second, and there are a couple approaches here, but what I settled on that works is, does this converge for x equal 1? I did better when I didn't get bogged down in the, does it converge to f of 1? That pooped me out. Converge to f of 1, does that mean it matches f at 1? Should I find f at 1? I could find f at 1. At the end of the day, I used the first part. The first part tells you all, does the series with x equal 1 converge? And I just stopped reading. Well, if you put in x equals 1 into this, what happens? You get, if you rewrite it, you get 2 minus 2 plus 2 minus 2 plus 2 minus 2. Does that converge? Does it converge? What's the first thing I told you to check for a series? The series cannot converge if the terms don't go to 0. And so the easiest way to go about this was to say that series with x equal 1 does not converge because the terms don't go to 0. Some people in the last class said, I thought they wanted me to find the interval of convergence and say, is 1 in it? That works. You can do that. You can do the interval of convergence, plug 1 in, and show what somebody in the last class said that wasn't true was diverges by oscillation. That's not good enough. I'm sorry, this oscillates 2 minus 1 plus a half minus a fourth plus an eighth. That's oscillating. And does it converge? Yep. Geometric clip. An R of negative 1/2. It converges. So oscillation, not going to cut it. Sorry. Anybody have questions about what they did? Okay. Well, that was one point. The answer was no with good calculus reason. Right? Doesn't necessarily have to be this, but it has to be some solid, foolproof, can't counter-argue it kind of calculus. All right, C then, rocking on to C. It says the derivative, and right away I started taking a derivative because I'm dumb. It says the derivative of log is that, but if I want to go from that series to log, don't I have to take the antiderivative? Now, you could do the antiderivative one of two ways, with indefinite integral and plus c, or definite integral and some very critical thinking kind of thing. Now, this is what I did. I said an indefinite integral. So if I want the antiderivative of that, then that means I want the antiderivative of the series. And I took the antiderivative. Now, if you do it this way, you must show a c. And then you must show clearly how you found that c. Not just, hey, you state c equals 0. Not good enough. You need to show how you found c was 0. I said let x equal 0. That proves that c is 0. And then I'm good. Now, another approach, bless you, is they said that, they said something like this. They used, I don't, this is not how I taught, so I'm still getting good at this. I can do it, but it's not my first thought. They said the log of 1 plus x squared is the antiderivative of that function, and they use definite integral. Now, if I want it to end as a function of x, then that means x would go in at the end, which means the function can't be x also. It has to be something else, dummy variable still, like maybe t. So they said, let me integrate from 0 to x, and they did the antiderivative of the series with t's in it. Just so many places for me to make a mistake if I do it this way. 2t cubed. And they integrated t squared minus t 2t to the 4th over 4. Did 4 terms from 0 to x, and then they put x in. That way is fine. All right. So, did you do one of those two approaches? Okay. If you did, then here's the deal. 1 point was for 2 of the first 4 terms. Now, rolled into that, I guess you would say, if you had any of those terms, sorry, this is my final answer with the c of 0 in it. I didn't actually scroll down. There's my final answer. X squared minus x to the 4th over 2 plus x to the 6th over 3 minus x to the 8th over 4. I did the general term because I'm an idiot. I don't think they would have even looked at it. If you did it right, who cares? Wrong. They didn't require it. So I just didn't read carefully. So if you got two of the first four terms, give yourself 1. If you got all 4 terms correct, and that includes finding that C is 0 in your work, then you get the other point. If you just never wrote a C and you just lucked out, that is not full credit. Okay? All right. Are we good? Did you get 2 out of 2 there? All right then. Here we go. Part D. Part D is the most valuable part to this problem. So you probably, if you're like me, you're reading this and saying, the series, part C, all right, so the series, make sure first of all that you use the series of part C, not the original or anything like that. So the log series. Find a rational number A. What the heck? A minus log of 5/4. I have no idea what they're talking about. It's less than 100. Well, great mathematicians talk to themselves a lot. So I hope you did something like, I have no idea what they're talking about. But then you said, what is this like? How is this like something I've done? How is it maybe different? What is it like? What are they talking about? Yeah, if nothing else, say, I don't know what it is. Log, what are they talking? I don't know. But they're talking absolute value of a difference less. It must be some kind of error, right? Well, what does A and log of 5/4 represent? Is this alternating or not? Yes. And I don't know about the 5/4, I'm not sure there. But what does A represent? S sub n. It actually represents a partial sum. And what does log of 5/4 represent? The real deal, true, infinite sum. Okay? So this is, I'm feeling like alternating series are bound. Maybe Lagrange, but I'm thinking alternating. Let's see. The first thing I had to do then is figure out, all right, log of 5/4, what does that have to do with the series I made? Well, log of 5/4 must imply that x is 1/2. So that was the first thing you had to do, is get a clue about what x is in the series. So I showed a whole gob of work, but at the end of the day, I said that x must be 1/2. That means you put 1/2 into the series. So instead of x squared, it's 1/2 squared. X to the 4th over 2 is 1/2 to the 4th over 2, and so on. So this is what the series would look like when trying to estimate log of 5/4. Cool? All right. So now the question is it alternating or Lagrange? It is alternating. Cool. That's better. I like that better than Lagrange. Next point of business is which term will work as my error bound? Which term is less than 100? First, second, third, fourth? Third. The third one is less than 100. Now, if that's my error bound, then my estimate needs to be S2. Okay? That then, S2 represents A. So here we go, then writing it up. A is S2, which is 1/2 squared minus 1/2 to the 4th over 2. A, or the number they asked you to estimate, is 7/32. That's my estimate. Now to show the rest of the analysis. Why is this less than 100th off? Well, first of all, they did not meet the conditions. You have to meet the conditions. This is an alternating series. When I go to estimate the log of 5/4, which is the series with not x in it, but 1/2 in it, that is an alternating series whose terms go to 0 and decrease in value. So it must be the case that A minus log of 5/4, which I hate that you're talking about that, you're confusing me, which is really S2 minus S. Does that matter that those two are switched? So usually it's S minus S2. Does that matter? Yeah, absolute value makes that a non-issue. That's why we put it in. And so is then less than A3. A3 needs to be found and verified it's less than 100. A3 is 1 over 192. Well, if the error is less than 1 over 192, doesn't it also have to be less than 100? Do that, Mr. Rickman, sure does. So that then is the last 3 points. The first point was, did you somewhere in your work say x is 1/2? Now, I don't know if I ever really, I honestly, looking at the rubric, I didn't have that blue. I don't know if I would have run that point. I never said, let x equal 1/2. I could have inferred it. I put 1/2 in place of every x, but I never clearly said, let x equal 1/2. So maybe I could have made that a little more clear. I knew what I meant, but that doesn't help, I guess, in Kansas City. So did you use x equal 1/2? That's the first point. Did you find that A is 7 over 32? That's the second point. Question in the last class was, what if I use more? What if I let S3 be my A? Is that good enough? Will their error be less? Yes. But are they doing too many, or basically covering their butt because they don't know calculus? Yes, they are, and you do not get full credit. A is 7/32, not more, not less. A is 7/32. And so they would not have got that second point. They could have, however, used the analysis to show the error in my analysis, which is way too many terms, is less than 100. So if on the last part you had the justification for alternating series error bound, if you had one of these two, basically the error is less than, then you said the error is less than A3. Then you found A3. Then you claimed it or showed it to be less than 100, then you get that third point. But if you're missing any of those components, you're missing too much. So you needed most of that. You with me? Give yourself 1, 2, or 3 out of, or 0, I guess, out of 3. And then if you got your 9, give yourself a hand. Give yourself a. Really? Here's your score up on the top. Yes, it says right there. Blink out of 9. It says right there. Give yourself a something out of 9. Ian, let me throw you down, brother.
I ran out of time on the last one.
Don't give me your excuses. What? There's no such thing as a frowny face out of time. But anyways, good. Nine? Not a baby. Oh, nothing? What? Oh, ouch. That makes you feel better, I bet. All right, then. That guy's going to MIT. Jeez, look at that. See, I bet you all feel better about yourself. You did better than the MIT guy. We'll practice, we'll keep practicing. My goal is that you approach the asymptote of perfection, right? So we're going to be doing this as time goes on. Like this, right? Except we're not going to just approach the asymptote. We're not going to be a little less. We're going to be on the asymptote of perfection. Am I right? I want a yes. Yes. Okay. All right. Let's learn. And by learn, I mean review. What time do we get out of here? 10 minutes. I'm going to review half of all calculus in 10 minutes. Here we go. Hope you learned well from this, Cannon, because your head's going to be spinning. We'll actually finish this tomorrow. No big deal. So, am I recording this? Oh, super. Okay. So, reminding you of the basics. Some of this is calculus ideas, but some of it is just test strategy or reminders of dumb points lost and things like that. So, would you recall back in the day, and this has been ideas since the algebra of the Middle Ages, change between 2 points over an interval. Now, there are a lot of ways to talk about change, but one is to say let x be the initial point, h be a delta x. Some books use delta x instead of h in the alternate in the definition of the derivative, which makes the second point x plus h, or x plus delta x, yeah? Now, if I then talk a rate of change between the two, then I want to compare the way the y changes or the outcomes change. Now, that might be position, or it might be just some generic function, over the change in x. Isn't that then rise, or the change in y values, f of x plus h minus f of x, over change in x values, x plus h minus x is, x plus h minus x is h. All right, now that represents change over an interval between 2 points. I could also look at this slightly different, and I could say, you know what, I'm going to let this be an actual constant point, not just any old point, but some nailed down constant. And I'm going to let the other point be a variable point. In that case, then the slope or rate of change between the two is f of x minus f of a for the change in y over x minus a for the change in x. Right? Or, if I really wanted to get creative, I could say, let some middle point be x, and I'm going to do a h or a delta x on either side. Now, if I go x below, or h below x, that puts me at x minus h. If I go h above x, that puts me at x plus h. If I find the change between those 2 points, then the rate of change is the change in y is f of x plus h minus f of x minus h over the change in x's x plus h minus x minus h. Now all that's great, and math basically stuck there, change between 2 points for 600-700 years. Then, in the 1600s, Leibniz and Newton's, several thousand a mile away, decided, you know what, I want change, not how fast it's changing at an interval, but how fast is it changing at that point. Now, if you do that, then you have to take that change between them, delta x, and make it smaller and find the change, and smaller and find the change, and smaller and find the change, and smaller and find the change, until that delta y over delta x change over an interval starts to approach a microscopic change in y, which we could call dy. And a microscopic change in x, which is dx. Now, think then the smallest possible triangle between 2 points you can make. The smallest possible triangle. That's then the derivative, the rate of change in that triangle. Now, derivative was a Leibniz name. Obviously, they're thousands of miles away, so they're not going to, the concept is the same, but they didn't call it the same thing. Newton called his a fluxion. You're really finding fluxions when you're finding a derivative, okay? But Leibniz sucks. Derivative 1, it's not a fluxion anymore. Now, the question is, how do you find a fluxion, or what the fluxion? So how do you find it? What do you do to take those 2 points close together? You take the gap h down to 0. Now that, actually, don't take for granted that that needed to be invented. That idea of a limit, that came first. They first invented the idea of what happens if something does this. That limit idea then led to the derivative. Now, when we do that, and I know we have a ton of shortcuts to avoid all this, but wouldn't you agree that gives us a rule for the slope or the rate of change at any point? And that rule is a new function based on you telling me at what x you want the slope at. I can use my rule to find the slope at that point. That rule, or the rule for the rate of change at any point, is what the derivative is. All right? Now, I could just as easily have said, you know what? I didn't really want a rule. I wanted the slope at 2. Well, if you wanted the slope at a point, couldn't you just as easily say, yeah, I'll still take the gap down to 0, but it's more like f at an actual a plus a gap minus f at a over h. That's still the first definition. It's just using it to find the slope numerically at a point rather than a rule at any point. You with me? Those are both the first definition. The second definition then said, you know what, I'm going to take this idea, and a, can a move to x, or does x move to a? X moves to a. A doesn't move. A is a constant. And so I would say, all right, get x closer to a, find the slope, find it closer to a, find the slope, closer to a, and then eventually you get this micro triangle, and that's going to represent the derivative. In that case then, a is a constant, so I'm finding an actual slope at a point, which is to say a numerical slope, not a rule, but a numerical slope specifically at some number. That then is done by taking x to a of the difference quotient As a third name of the derivative, I forgot to put it in. Would you throw in the nerdiest name for the derivative? One phrase for the derivative is instantaneous rate of change. One phrase is tangent slope. The nerdiest phrase is the limit of the difference quotient. Hey, what's a derivative? Oh, what's the limit of a difference quotient? The difference quotient is the slope. The limit, as the 2 points get closer together, then makes the derivative. Last but not least, if in this case you wanted the rule at x, then rather than move one point, you're actually moving both points closer on either side in an equal distance on either side ways. So we'll call this, well, this, by the way, is called the alternate definition. If we move on both sides, that's called the symmetric definition of the derivative. And it involves, kind of like the first one, taking the gap, which is h, down to nothing. So the limit as the gap goes to 0 of difference quotient. Sorry, what's the denominator? If it's h on both sides, then altogether the change in x is 2h. All right. Are they cool? All right. It is important that you recognize some definitions of the derivative. The limit, say this one is a classic. The limit as x goes to 1, maybe, of arctangent of x minus arctangent of 1 over x minus 1. Maybe you're looking at this whole and you say, well, it's a limit problem. I could try and direct substitute. How does that come out on direct substitute? Top is arctangent of 1 minus arctangent of 1. That's 0. Bottom is x minus 1 or 1 minus 1. That's 0. When you see 0 over 0, yes, you could go in a L'Hopital direction, but you might also be wise to consider maybe this is a derivative problem. Because every derivative is change in y over change in x approaching 0 over 0 change in y over change in x. That is the case here. You would be wise to say, well, this is the derivative of arctangent at 1. Now, would you be surprised to hear that a lot of people write that on their paper but still miss this question? And the reason is because then they forget to actually take the derivative. And they would say, this is arctangent of 1, and they would go with the multiple choice of pi over, what's arctangent of 1? 4. Right, good job. Okay? They would choose pi over 4 because they say, oh yeah, arctangent, I got you, arctangent, and too fast. Is that the answer? No, what did they forget to do? They didn't actually take the derivative. So then take, after you said take the derivative, then take the derivative. And the answer is 1.
Sydney Goldline, please go to the
All right,
library.
we'll finish tomorrow. Have a lovely day. 7th period is long. You have 5 minutes, not 10. You have 5. But I'm sure you could show up late and say, I didn't know it was supposed to be 5 minutes. As long as it's not my class. Oh, shoot. Here's some more.
I am not doing it. Every time you correct it. Yeah, I will. You need to how many times you correct.
I didn't do anything.
Faster than. It was due.
That's good practice that you didn't get good practice on it. You need the practice. If I were you, I'd go back and do some of those because you need it. All right. Have a good day.